There we are. Okay, in 1907, a social hygienist by the name of Sybil Neville Rolfe founded the Eugenics Education Society. She was influenced by the writings of Sir Francis Galton, who was a Victorian polymath and a bit of an expert really in a lot of areas. He was the founder of the modern eugenics movement, and who actually coined the eugenics term back in 1883. But what actually is eugenics? Eugenics is the study or practice of attempting to improve the genetic quality of the human population by selective breeding or other forms of intervention. Eugenics quickly became really popular with fashionable among intellectuals and also policymakers. And also the Huxley family took a keen interest. And if you know, Aldous Huxley was the author of Brave New World, which is a stark warning about an over-engineered society. And his lesser-known brother, Julian Huxley, was the secretary of the Eugenics Society. Their grandfather, Thomas Henry Huxley, worked closely with Darwin himself and was known to be the bulldog of Darwin. Darwin was apparently very quiet, and then Thomas was the mouthpiece of the pair. The darkest chapter for eugenics came in the 1930s when Adolf Hitler started to take a keen interest for his Aryan master race policy back in the 1933. And obviously the Nazis weaponized this eugenics movement. And so after the war, they needed to rebrand. And then Julian Huxley decided to rebrand it under transhumanism. So transhumanism then carries the same belief as the original eugenics movement, that we should use science and technology to transcend our biological limits. And the impulse to improve humanity never went away. Today, transhumanism isn't philosophy, it's $1 billion longevity labs, biohacking communities, and Neuralink. But the tools are different. AI and genomics are colliding, and to understand what this means at a biology level, I'm going to hand you over to Simon.
It was very prompt, Jerry. I'd just like to say Jerry made the request for the Britney mics, or as he calls them.
You did Britney, I did Madonna.
Madonna over here.
Britney, Madonna.
So, anyway. So, inside the DNA of every cell in your body, and you, me, everything, and even in Jerry, there's a universe of potential. So your life and the world around us runs in code. So you can call DNA as the source code. I'm used to having the stage up here, or the slide up here. So DNA is the source code, but from a sort of computer speak, RNA is really the runtime. But the cool thing about this is nowadays we can actually, we have the ability to read that, right? So I spent the last 15 years working in the area of sequencing stuff. Sam talked earlier about how they send stuff to space and send it back. I run a lab that sequences some of that stuff. I've spent the last 15 years trying to work out how we can do that faster and make the data more accessible. And it turns out now, when we've got tools like AI, if we can make data more standard and accessible, we can do amazing things we'll talk about in a minute. So if AI is kind of what we're all talking about here today, that kind of programs how we think nowadays increasingly. We spend our time using AI to help us think faster. Genomics is kind of what actually programs everything about us and our existence. So if we go back in time, back to Jerry's Darwin thread. So Darwin and Mendel up here, they gave us kind of the conceptual OS, so hereditary and genetics, okay, and inheritability. And then we've got Franklin, and I've made this, EDI now. So Rosalind Franklin did the X-rays, and Crick and Watson got the credit because they took her results and interpreted them faster than she could. So they gave us the sequence of DNA, okay? And this is Fred Sanger holding up a radiograph where he's manually reading out the sequence of DNA. So he invented the way that we read DNA. And this is Carey Mullis, and he's a much cooler character than all these guys. So he's wearing his nice flamboyant shirt. He invented the PCR reaction, apparently after he fell off his bike after taking LSD. And last but not least, we have Craig Ventnor. So in the noughties, we had the Human Genome Project. That was a $3 billion international consortium to sequence a whole human genome and do some other stuff and build the methods actually to analyze our genomes. Craig Ventnor, he was a good disruptive entrepreneur. He sequenced his own genome for 1/10 of the cost. Okay, so he came in, he exploited the technologies that had been built off the back of the Human Genome Project, did it faster and quicker, okay, because he came to the party late and used the technologies they involved. Fast forward to the 2010s, and this is when I kind of got involved in genomics. Next generation sequencing came on board. That wouldn't have happened without all these technological developments over the last 100 and 150 years. And now, this is what we termed at the time Flatley's law. So this is the cost per genome on the left here versus Moore's law. So the cost of genomes went down dramatically as these technologies evolved. So on a log 10 scale, massively outstripping the pace of compute. And it's interesting we follow on from quantum computing, because quantum computing, some people think, is how we are going to be able to do sequencing at scale. So that brings us to today. So today we're sitting on a database of around 40 petabytes of data of genomics. A lot of this is in open source. We can access it, but it's very fragmented and siloed. But that's doubling it year on year. So this year we'll sequence more than an entire database, okay? And that's where it matters to us. So if you think about it now, all we heard today, it's quite interesting coming to an AI focus meeting, is about the problems with AI, etc. All we hear all day now in the media is about synthetic data, the internet's being swamped. So how are you going to train these models? The cool thing about genomics is we can take a sample from anywhere in the world. We can find new stuff if we sequence deep enough, okay? So there's a massive bank of data. This is real pure signal from the physical world. We increasingly can understand that better. We can exploit it. We can use it to monitor things. We can use it to monitor how the environment responds. We can use it to make the environment more greener as well, right? We don't have to just use it to engineer GMOs. We can actually monitor how pesticides work, how we find pests and deal with them, etc. So really, you've got this massive data set. We've got this. The world is a living data set of 3.8 billion years of evolution that we can now start to leverage with these technologies. So kind of like biological tested production code. But the problem is, we can have all this planetary data, and we can access it at scale. And there's massive companies just going out sequencing bits of the Earth at random to find new things. But every lab speaks different dialects. All genomics labs, Sam talked about this earlier, how we interact on these kind of data is very fragmented, okay? This is kind of the way AI was, maybe a decade ago. So models were trapped in labs until APIs, cloud standards created, and the internet, in fact, created the resources for us to train these models on, and they've ultimately led to the sort of ChatGPT moment. So genomics, I would say, is at that same inflection point where we need to have better connectivity. So if we can have the equivalence of AI, APIs, cloud, and standards, we can have this sort of ChatGPT moment. And where that's going to take us, we're at that tipping point. So genomics won't make this leap without same sort of standardization that unlocked AI. So we need to integrate this across the whole supply chain. So how we build genomics infrastructure that connects with AI, compute, and synthetic biology, the way we can reprogram this, is by integrating this into the real world. So not just having computers sitting in AWS processing data for people remotely. We need to build this into devices that sit in the real world, feed back information in real time, and then use these genomic endpoints as actually the test signals rather than just having single point measurements. And we've already seen the impact of when this works, okay? So take protein folding. So protein folding is a classically MP hard problem that people have been working on for decades. We had a Russian space scientist in our center who used to work purely on protein folding. But with enough shared data and benchmarks, so as data was put into public databases and enough compute power and the power of Google as well, DeepMind, they solved this in 2020. So the first AlphaFold was published. We're now on to AlphaFold 3. And this has created at least the starting point. It doesn't solve every problem, but it takes the first 3/4 of the problem is solved for protein folding. So if you work on a new protein, you can fold it on your phone now. It doesn't get you the whole of the way there, but it gets you 80% of the way there. So this is biology sort of, I guess, like an ImageNet moment, where proof that when AI meets standardized omics, unsolvable problems can collapse. So an AlphaFold is just really the appetizer for this. So AlphaFold predicted structure. Next, we talked earlier about digital twins, so simulation and design. So imagine your digital twin with access to your genome, testing treatments before you take them, right? That's not that far away. Virtual cells running millions of experiments in silico, only synthesizing the winning compounds, right? So we can fast track how we develop new things. And biology then becomes more of a programmable asset and infrastructure. And this is how we move from reactive science, where we measure the things around us, to where we move into more proactive design. And that doesn't mean designing new things that are genetically modified. That means designing personalized information. You can give your own ChatGPT your genetic information. It'll know all your behaviors. It'll have read all your emails. And then you can allow that to help you train your daily life as well. So this isn't a distant future, right? So AI detecting infections before they happen from your RNA, that's going to happen in a very near future. Farmers optimizing yields with RNA-driven dashboards when they go out and send out a test from their lab or their farm to be measured. Cities tracking pathogens in real time through wastewater. This is actually happening. It's just not happening at scale in an automatic, integrated way yet. Okay? So this sort of intelligence layer isn't just coming, it's here. You know, you can imagine kids running genomics experiments on their phones like a calculator in the very, very near future. But the breakthrough isn't about more data and more dashboards. It's actually about how we embed this across discovery, production, supply, and monitoring. So how we make a connected intelligence layer for biology. So that kind of gets you to the question is, what happens when this sort of operating system of life can merge with the operating system of intelligence? So when AI doesn't just analyze the biology, but actively programs it. So Jerry's going to talk about this next.
Thanks. So as you all know, or some of you may know, the AI classification, AI falls into one of 3 classifications. So first one, artificial narrow intelligence, is also known as weak AI, designed to perform a specific task or narrow range of task across pretty much a single domain. We did some work with a company called A&L Goodbody, who have in essence, a generative AI system called Harvey. It's a Silicon Valley startup named after Harvey Specter, Harvey Suits, very original. In essence, it's a ChatGPT model that's just fine-tuned on law, and following on from Nathan's session there. So that would be a form of artificial narrow intelligence across a single domain. And we're seeing a lot more of that, also known as vertical AI. Next one, as we all know, artificial general intelligence is a type of AI that possesses the ability to understand, learn, and apply knowledge across a wide range of tasks to a level comparable to a human. And this is like what all the foundation models are after these days. We're all getting to AGI. You never heard this term really a lot 6 months ago, and now you're hearing it every day, the path to AGI. The third one and final one is artificial superintelligence, and I've even started hearing this one now. And this is a theoretical form of AI that surpasses human intelligence in all aspects. And then when we get to superintelligence, or if we get to superintelligence, we enter something called the technology singularity. It's a mathematical physics principle where equations break down. And if we get to this point, then it's no longer to the point where we can no longer be controlled by the human race. Although superintelligence has been around for a while, there's been rumblings about superintelligence since the 50s. Superintelligence was really brought to the forefront back in 2014 by a gentleman called Nick Bostrom. Nick Bostrom is an Oxford philosopher, and he wrote a book on the very subject, superintelligence. The main thesis of the book were how do we get to superintelligence? And in the book, he discussed 5 paths to reach superintelligence. So the past, I'm going to talk about each one. I'll probably talk about AI more. So throughout the history of AI, there's been 2 opposing camps. You had on the best way to create artificial intelligence or simulate human intelligence. The first camp were known as the connectionists, and it all started back in 1943, where a gentleman called Warren McCulloch, an American neurophysiologist, teamed up with a sidekick called Walter Pitts. He was a homeless mathematical deep genius. Together, they created a mathematical model of the brain, giving birth to the artificial neuron. That neuron was then taken and developed into the perceptron in 1958 by a gentleman called Frank Rosenblatt. The perceptron, in essence, was a simulation of a neuron that could carry out a mathematical binary classification. And this is the first time of AI and the start of the neural network. From there, it grew into the multi-layered perceptron, which is more neurons, and then into a feed-forward network. Then Jeff Hinton took over with a gentleman called David Rumelhart in the 80s, and then started to build in like backpropagation and other elements into this neural network it was becoming. And then it became deep learning as in 2007, and that's what we know as deep learning. So that's kind of the neural side, and then the connectionists. The other guys are the symbolists, and they believe that intelligence would be built on facts, rules, and logic. And it was headed up by a gentleman called Marvin Minsky, who was part of the Dartmouth Summer Project guys with John McCarthy, who was one of those. And he's been a real advocate for this symbolic kind of side of life. So these two kind of camps have been playing out for quite a while. They still are. But there's also a third that there's playing out, carving out, and that would be by Demis Hassabis. You've probably come across him quite a lot. DeepMind, 2010, London startup, obviously Google acquired it back in 2014. These guys believe in kind of a hybrid approach, and they combine symbolic kind of reasoning with also sort of connectionist kind of pro-neuro network techniques. And Simon mentioned about AlphaFold, but as you know, they did one in 2016 called AlphaGo, which was a to play the world champion of Go, Lee Sedol, and Go. Anyone play Go players here? Jordan, you're a Go player. You look like a Go player. A really hard strategic game, and they combined and they beat him, which was quite a shock to the Go community. And they combined 3 techniques to create this system. The first technique was deep learning. I've just covered that, neural networks. But also they included reinforcement learning and combined these two together with a technique called deep Q learning. But then they also added another one called Monte Carlo tree search, which come from the Monte Carlo methods, which were devised back in the 1940s as the Manhattan Project team. They created this mathematical algorithm to model the behavior of neutrons in a nuclear reaction, and they used that for probability and randomness. So that's DeepMind, and then you've got OpenAI, which is obviously LLMs. They believe in scaling. They're pure connectionists. They believe in scaling laws. Okay, if we throw enough compute at this, throw enough data at this, intelligence is going to emerge just by magic. So I'm not too sure. I waver between these two. That's the first path. Don't worry, I'm not going to talk about that length because it's AI. I'm going to talk about AI more. But I'm going to talk about the next couple here. Whole brain emulation. This is where we literally replicate our brain and upload it, a digital version of ourselves, like a digital twin kind of concept called uploading. And they reckon we're not too far from that. The next one, biological cognition, and this is where we get into Simon's territory. This is kind of like selective breeding, genetic engineering. We look at embryo selection and stem cell sort of creation, etc. This is a path to superintelligence, but it's going to take many, many years. They can speed it up. Next one, networks and organization. There was an essay out in '93. A guy called Vernon Venge, sci-fi writer and computer scientist, wrote this essay called "The Coming Technological Singularity." In there, he said superintelligence could come from not just one mind, but a collection of minds, and that could be humans and machines, not linked together by information, and then which could be construed as the internet. In essence, the collation of a centralized source of data, by putting an intelligence layer into that could become a form of superintelligence, and kind of like a global brain. It's kind of like that's what LLMs are, really. So it's playing out. And the last one I want to talk about probably for the remainder of the session is brain-computer interfaces. A high bandwidth link between our brain and machines. So I'm glad the Ada Lovelace guys aren't here. They'd probably grab me off stage. I can't say for certain what Elon Musk had on his desk in 2016 when Neuralink was founded, but in my opinion, Nick Bostrom's book, Superintelligence, was highly influential on Elon Musk creating Neuralink back in 2016. Because 2 years later, Neuralink was launched, a company that's whole mission is to create that human brain machine interface. Now, you really wouldn't want Elon Musk anywhere near your brain, or you wouldn't really want to go anywhere near his as well, really. But let's remove Musk for a minute and look at the science and the art of the possible. In fact, even in August there, Sam Altman pipes up and says, right, okay, I'm going to create a rival to Neuralink called Merge Labs. And ironically, Neuralink and OpenAI shared an office back in 2017, so obviously Sam Altman's robbed this idea, and it came from a blog post called The Merge, merging ourselves with the machines, back in 2017. Now, you wouldn't want either one of these anywhere near it, these two maniacs. But so what is Neuralink? Well, Neuralink is a high bandwidth bridge to create a high bandwidth link between humans and machines. But why do we even need a high bandwidth bridge? Because there's a massive imbalance between what goes in the speed that information goes in our brains to the information that goes out of our brains. It's an input-output kind of concept. Our input is broadband speed. We Vision alone takes in 10 million bits per second, but our output is like dial-up 56K modem speed. Our typing is 20 to 30 bits, and our speech is 50 bits per second. So you can see there's a massive imbalance input-output. So how does Neuralink work? Well, at its core, Neuralink is a tiny implant that goes and sits in the skull. From the implant, there's little threads that go thinner than human hair that go into the surface of the brain. These threads pick up neurospikes, the electrical signals that neurons naturally make. And then a custom chip inside the implant then records those spikes, cleans up the signal using adaptive filtering, and then sends it wirelessly to a computer, and where it listens for different sets of neurons. In essence, it's a mapping exercise. That the implant is there to record the signals. The signals then are mapped to certain actions with hands, etc., and brain. So then it allows the participants to be able to type a letter, move a cursor, or operate a machine just using their mind. The first successful trial was this guy, Nolan Arbor, back in 24, so it was not long ago now, only last year. This guy was paralyzed for many years after a diving accident, but even he had the daily procedure, and then the day after, he could instantly start controlling a cursor and his laptop using his mind, literally a day after. He was the first, but he wasn't the last. Over the last kind of year and a half now, there's been 7 participants, and they all call themselves like P1. Nolan's P1, and then the last guy, June, just gone there, is known as P7, so participant. And the real-world use case is, in essence, people with paralysis to be able to play a game or move cursors or operate a machine using their mind. And here's a little clip. Oh, got the sound, Ben?
We actually have a whole community of users.
Oh, let me go back again, I'll come back.
Here we actually have Nolan playing Mario Kart. Now, what's special about this particular clip is Nolan is not the only cyborg playing Mario Kart in this clip. We actually have a whole community of users, as mentioned earlier, and this is literally 5 of our first users of Neuralink playing Mario Kart together over call.
Every one of those players is paralyzed, depending on there's certain levels of paralysis. But with this implant, they can interact with digital systems at a speed the same as everybody else. What I find the mind-blowing aspect is the machine learning model, or the silicon neural network on the right, is inspired by the biological neural network on the left. And I just find that fascinating. And it's extending the fundamental substrate of the brain. In essence, we are literally connecting biological intelligence to synthetic intelligence. So where are they now? So first of all, is telepathy, the product which you've seen in action there with the participants. Let's paralyze patients, control a cursor, type, or play games by thoughts. Already being used by about 50 to 100 hours. Next one is blind sight, to restore sight by integrating into the visual cortex. Trials in 2026, and future applications, speech decoding, robotic limb control, psychiatric disorders, neuropathic pain. So what are the possibilities of this kind of technology? Just take Elon Musk out of the equation just for a bit. So here's combined thought-to-thought communication, mental text message, i.e. by integrating to a certain part of the frontal lobe where thought is converted into words. And so you can create a message in your mind and then map it to a haptic in your hand, say, when I click my fingers to send the message. Next one, shared sensory experiences, stepping into someone else's mind. Imagine you could read the mind of your partner, your husband, your wife. Imagine that. Or do you want to really imagine that, really? I don't know. Interesting concept, though, isn't it? Next one, skill upload or skill download, instant skill, like the Matrix. Learn a skill kind of instantly. And even remote presence, inhabiting a robot body over the other side of the world. And this could become a real possibility. And we're really getting to avatar territory there. So now we come full circle. So this session comes down to convergence, AI and genomics and neural interfaces. Simon has shown us how genomics and AI are rewriting the code of life. I've shown you AI and neural decoding are writing the interface of the mind. And that convergence brings us back to the deepest question of all. When intelligence enters our body and our biology is programmable, what does it mean to be human? Simon.
Thanks, Jerry. So it's interesting, when we were preparing for this, we both came around to this sort of convergence piece. Me coming at it from the technologies that converge to support like what's going to be the next wave of genomics, which is AI, synthetic biology, cloud compute, plus obviously the data sources. So Jerry started talking about Darwin and Galton and this sort of impulse, meant over 100 years ago to re-engineer humanity or the world around us. We saw how that was sort of twisted in eugenics. There was a slide Jerry did take out for political reasons that you can tell you about afterwards, which toned that down a little bit and made Elon's gesture look a little less menacing. But my thread's been genomics. So what this idea of like we're all sitting on this operating system of life is how we're built and how our brains are constructed and how our brains learn, just like the computers we're now building. So Darwin and Mendel, they kind of give us these principles about how this operating system could work. So it's more of a theory at that stage. We discovered the sequences, so that now we actually know how is this programmed. Actually, the bit I've focused on is this idea of RNA as this sort of intelligence layer that helps translate that code into the real world, because DNA can't do anything. Okay. Actually, a wise person at a conference once said about sequencing cancers was, it doesn't matter about what you've sequenced because that's no longer in the patient, right? So then we've moved on to like sequencing people. One person took 10 years. It took a lot less time to sequence Craig Ventnor. He's sequencing all the stuff around him. Now you could be sequenced overnight. I could take your DNA now. We could probably do it, in 2 or 3 days, and you could have the data back. Problem is that might only cost $100. How you analyze it, interpret it, that costs infinity, because we can't even do that for one person at that point, because we don't have enough data and we don't have enough information to, or context, as we now, people talk about, context, prompt engineering is now context engineering. I think that's really, really crucial. So, but we are seeing glimpses of this breaking into everyday life. So everyone in the room knows what PCR is now, right? Did you know what PCR was 5 years ago? No, right? So I didn't even need to explain what PCR is because of COVID, right? And one of the, genomics had its moment in COVID too, because we were in Queens, we were running this, but globally people were sequencing COVID at scale, tracking these different variants. All these variants you hear about, they're being tracked. They're happening in university labs all the time. Okay, so that's one of these sort of moments where this sort of technology comes into the zeitgeist, right? But genomics hasn't had its Facebook moment yet, and I saw a wise person said, until people can monetize it, the internet, didn't get monetized until almost the time of Facebook, where it really become commercially viable that the internet was going to make huge amounts of money, and then you lose control of it, right? AI is having this inverse adoption curve where it's in the hands of everyone now, okay? And now we're working out how to monetize it, and I think OpenAI have a pretty good approach. As of yesterday, launched their assistant that will pick what you buy for you, as far as I can tell. So the point in betting, this is coming really, really fast. And I think it will be an inverse adoption curve for genomics, because I think within the next 5 years, you'll all be sequenced at birth because it's cheaper than doing PCR tests for childhood conditions. You will have your genome available. In Northern Ireland, as of this year, you all have your electronic healthcare record. You'll be able to ask for access to any of your data, and you'll be able to do whatever you want with it, right? So you're going to want to have your OpenAI chatbot to be able to interface with your genome if you choose to do that, right? Whether it can give you useful information, but that's really up to your choice. And you can already see this in medicine, where support vectors that can give you individualized care are not better at diagnosing, but they can help you better manage it in your own context. So giving you the information plus the context, and that's where you get this convergence of all these technologies, which is going to underpin the next sort of wave of the next industrial revolution, I think. So that's it for now. Thank you for your time.